Hi, my name is Ryan Thompson, and this is my submission for CPSC 5210 Computational Geometry. We'll be covering some basic concepts of computational geometry, which all stem from the first section of line segment properties. Each of the following sections build off these basic concepts developed in the first one. So after we have an overview of the section 1, these slightly different or these different algorithms to look at different ways to look at a set of points. After looking at each one of these, some runtimes and different descriptions will be applied. In the first section for line segment properties, we'll review some terminology, explore the cross product, look at what the definition of a turn would mean when encountering two line segments, and what the intersection can help us with, or the intersection of two line segments can help us with. Line segments. Here's some basic terminology. If you let P1 be denoted by x1, y1, and P2 be denoted by x2, y2, then you have defined two distinct points in a plane. The convex combination series, or it's really a scalar representation that can be applied to P1 and P2. So therefore, P3 falls somewhere on this line between P1 and P2. Again, or alpha, represented here as I just referred to as the scalar, must range between 0 and 1. So if alpha was 0 here, it would have no influence from P1 and be 100% from P2, or P3 would equal P2 in this case, or vice versa. If alpha was 1, P3 would equal P1, and it would lie, the second point would lie on P1 and have no influence from P2. If alpha was 0.5, or exactly halfway between 0 and 1, this would be a point, P3 would be a point between P1 and P2. A line segment. It's a set of convex combinations of P1 and P2, again, are two distinct points. So P3 is some alpha combination. You could have a beta that was a different level between 0 and 1, which would give you a P4 that is somewhere between P1 and P2. But it's also on this line, so it's collinear, the combination creating a line, collinear between points P1 and P2. Something right now to note that we'll get to in the directed segments is P1 and P2, when they are labeled as a line segment, it just indicates a series of connections between P1 and P2. It doesn't indicate in which direction you're actually moving. Important later. The endpoints. Given a segment P1 and P2, which we just learned the definition of, then P1 and P2 are the terminal points for that segment, or they're the absolute boundary points for that segment. Now, as I pointed before, in a convex combination, you could have alpha set to 0, where the point could lie on P3, could lie on P2. But the 2 points that when you actually label these 2 points, P1 to P2, that's what you're accounting for. So even though there could be a point on the endpoints, once you've given this designation, P1 and P2, that could be considered your origin at some point. But that's what's important to note, is that in this notation, P1 and P2 represent the ends of the line. A directed segment. Directed segments are given a specific ordering of 2 distinct points that form a line segment. So this directed segment is P1 first, endpoint 1, endpoint 2 is P2. If you had P2, P1, the line, this notation would be reversed. It'd have P1, P2, but the line segment would still be going to the right. That is your general notation. So the line segment P1, P2, or the directed line segment P1, P2, also indicates which comes first and which comes second, a vector. If the directed line segment starts at the origin, 0, 0 generally, then the directed segment can be treated as a vector P2. So when you have a starting point for the vector and a direction for it, so if the origin was P1 and P2 was some other distinct point, then moving in that direction from the origin to P2, you would have the directed segment also considered a vector. The cross product. So let P1 and P2 be vectors. So again, to review, origin, then the line segment, the directed segment from origin to P2 and origin to P1 would be a vector. And that fits the definition as described previously. Now, the cross product is defined as this X is really a cross product symbol. It's the determinant x1, x2, y1, y2, or simply put, x1 times x2 minus x2 times x1. So if you take this plane, defined here, your standard xy coordinate system, and you have the directed segment P0 or origin to P1, and you have the directed segment origin to P2, taking the cross product of the two, so some type of influence of P2, some type of influence of P1, and you'll get this point out here. This signed area, or the area covered by both of these vectors and the cross product of the vectors, give you this area below. And this is going to be important later when we talk about the distance between points or the distance between lines and what really, how would you determine which is the direction that you're going. So all of these points will be used later. So right now it's important to note that you can find some type of area between two vectors, and that way you can quantify the difference between two different vectors and their cross products by the signed area of the vectors. Turns. So again, here's our notation for our cross product. If the cross product is greater than 0, then P1 is clockwise. Again, this order is important. In this ordering, P1 is clockwise from P2 with respect to the origin if it's greater than 0. If the cross product is 0, then P1 and P2 are collinear and they lie on the same line. If the cross product is less than 0, then P1 is counterclockwise from P2 with respect to the origin. So you can always, of course, have an angle between them, which is defined with this notation. The angle, what is your starting point? Here's a vector starting point, and here's your second vector. And this notation is really the difference of P1 cross product difference of P2. Now, in general, why did you not see that applied before? And that's because we started at 0, 0. If P0 was not the origin, this is the adjustment you would need to make to be able to evaluate the cross products starting from a given point. And this general definition fits the specific case of the origin, but it also allows us the flexibility to evaluate when we have a set of points that are randomly spaced throughout a surface. So taking these three criteria and trying to give them a graphical example. If the cross product, this area, is greater than 0, then we have this clockwise rotation. So P1 to P2, it's going to rotate to the right, or as a clock would also rotate. 0, again, it's collinear, and the two vectors lie in line with each other. Now, if the cross product is less than 0, then P1 would have to rotate the opposite direction of a clock's rotation, or counterclockwise, to get to P2. And these are all important criteria later, especially when we look at a convex hull that relies on this notation to keep a standard of criteria evaluation between points. The intersection. If and only if either or both conditions hold, each segment straddles the line containing the other, or if and only if, an endpoint of one segment lies on the other segment. So here's the endpoint, 0, lies on the other segment. And in all of these examples, clockwise, counterclockwise, collinear, they do intersect because origin, considered the endpoint of each of these vectors, lies on both. So based on this intersection definition, each of these vectors do intersect. So keep in mind this terminology because all of these definitions are used in later sections to define and speed up a brute force algorithm to a more elegant algorithm. Intersecting line segments. We'll start with some basic terminology again of the intersecting line segments. At T1, A and C are comparable, but not B. At T1, A is above C. So what does that mean? What exactly can we translate these definitions to be useful when evaluating line segments and their intersections? So again, let's review. At T1, A and C are comparable, but not B. Think about this terminology. You have T1, which in this case actually represents time. This is one of the few algorithms that we'll explore in these 4 sections that actually takes time into account. All the other algorithms really deal with like fixed point sequences. Once P1, say, is fixed, it occurred, we're not really concerned about when it occurred. We just know that it occurred. So when you're looking at these intersecting line segments and using the sweeping algorithm, you're really concerned about at what point in time are these occurring. And that informs you if you can compare something or not. So A and C are comparable, but not to B. So here's line segment A and line segment C. They each have their own unique endpoints. So at T1, we create this vertical line, which looks like our x-axis and for time. And we create this vertical line, and we look to see where it intersects. Is that any endpoint, so here, T1 all the way up to the top, at any point, would it cross line A or line C? And it does. So we can compare line A and C, but not B, because at T1, it is not comparable. It does not have a point that intersects this vertical line. The second terminology unique to this section is at T1, A is above C. So again, on this line segment, A comes before C. And when I say comes before, we look at the endpoint ordering. So if A and C ended together, we would go to the first point to determine. But here, A is above at this segment. Line A intersects the line above line C. So A is above C. And this is the terminology here. This symbol is the above, and the T1 designates at what time interval this occurs. So if we had another time segment out here, you would have a different intersection. You'd have a different line segments to compare to. And here's a little bit further example. When you order by sweeping, you pass from left to right. Now the book has some pseudocode on page 1025, but that pseudocode is very general to give ideas about insertions and other points. So I feel it's a little more useful to look at the graphical example here to to really relate the point that how time is functioned into this algorithm. So again, the x-axis is treated as time. Time for this algorithm is if you were to sweep through all intervals of time, actually it doesn't really determine on time, it determines on the number of line segments that you have. So n is the number of line segments, again base 2, and the lowest runtime is n squared, where n is the number of segments. So here we would have 3 segments, so 3 log base 2, 3 is our uppercase, and our lowercase is 3 squared, or 9. Having this methodology, you can see at different time intervals, we have a different set of comparable line segments and a different, in this case, which ones are above each other. So at T1, or T1, is above line C, and it's also comparable. Now, line B is above line C, but not comparable at T1. So now progressing to T2, extend the vertical line up, and now you intersect 3 lines because a unique point is found along the vertical. And now we're looking at the ordering. So which one came first? So A endpoint came before the B endpoint, which came before the C endpoint. So A is above B, which is above C. So again, this relationship shows the order of intersection here. If you go to your next time segment, T3, you can see now A no longer extends or has points along the A line segment no longer intersect the vertical line of T3. So now only B and C at T3 are comparable to each other. So in T1, A and C are comparable, and at T3, B and C are comparable to each other. So this algorithm lends itself to some other basic ideas of time scheduling and event point schedules. So when exactly do these occur and at what times actually becomes important, which is very good for ordering or queuing events. Stated before, other ones just simply look at if the point exists or does not exist in a set of points. They don't actually consider at what time do they occur, so that we can compare some if we can determine if they're comparable or not to each other. One thing that is not in this example, but obviously could happen, is that you have 2 lines intersecting times one is above the other. So that's another interesting point to note, because time changes which is above or which is below and which is comparable. So again, in this algorithm, it's not so much the time frequency that plays an issue with the run times, it's the number of line segments that you have that you must evaluate. Because as one has a fixed endpoint, you'll be able to calculate the intersection of the two again. And we'll review the definition of intersection. It's if the segment straddles the line, so if it crosses the vertical, here as A crosses T1, or an endpoint of one segment lies on the other. So if B had started on T2, it would also count as an intersection. So it still fits our previous definition of intersection. Convex hull. So before we start this section for convex hull, let's go back and review a description of what convex means. So convex combination. So you can have some scalar applied to 2 points, P1 and two distinct points, P1 and P2, that create P3 that fall along that line. So that's our definition for convex combination. Now the whole you can think of as an envelope or this surface area after you've taken the combination of points. So let's keep that in mind as we explore what a convex hull is. Terminology. Points. CHQ is a small, given a set of Q points, CHQ is the smallest convex polygon P for which each point in Q is either on the boundary of P or in its interior. So again, the point of the convex hull is to minimize this surface area while still, and I say surface just because we're generally dealing with XY coordinates. But again, if you extend to higher definition, surface is not a limiting term. So given a set of points in P, here we have P1 through P8. And if you wanted to find the smallest convex hull that enveloped each of these, that is what this goal is. So what here again, P1 through P8 are all elements in Q. Hull, as you go around each point, your goal is to minimize the distance that you have to cover. So this may sound a bit like a traveling salesman problem, which it could be, only it doesn't have the definition on which points has to come in order, simply that once starting at a point, you'll evaluate its distance. Also, you'll evaluate the cross product. Here, you'll evaluate the cross product and get this area. Once you have the area, you have a quantifiable measure as to which of these will give you the shortest path while still covering the other ones. So here, this points out that P3 and P5 are not on the boundary condition, so they are not part of the convex hull. So if you had to write this, the convex hull is always a subset of Q. Another requirement for the convex hull is that you need at least 3 points. So you would use a simple method like triangulation to come up with your convex hull. But again, you don't want to limit yourself to think in terms of only one geometric object. Looking at these in terms of polygons is probably the most flexible because it allows you to have obviously a varied series of edges to come up with this minimal envelope, but still cover every point that you originally given in Q. If you were to connect every point instead of just the edges, and you looked at the total surface area covered, it would not be the minimum, in which it could never be, because you're doing redundant lines. If you were to connect P4 to P5 and then P5 to P3, you would have this additional line area, and you would not have the minimal set. So each of these, there's 2 algorithms the book uses to describe this approach to minimizing the area. But that's the goal of each of them. But now each approach gives you a slightly different runtime as a result of its implementation. The first one is called gram scan. Now its runtime is O in log n, and n here is the number of points, where previously on a sweeping algorithm, n is the number of segments. Here we don't know any line segments because we have to go point by point, our distance and our criteria. If you go point by point, this is a very long method, and you can see the recursion because once you're in a point, you evaluate all other points every time. So that's where the log n comes from. The final points in the convex hull are in order of counterclockwise appearance. So going back to review, counterclockwise, once you have a point and you extend out from your line segment, you're looking at the cross product to determine if it's less than 0. If it's less than 0, then you can evaluate that point and move on. This is not a trivial condition because by going in a counterclockwise order, you're hoping to land on these outer segments every time and evaluate the angles between each of them. So again, you can always evaluate the angles, even if you're not at the origin, by using this offset. And now once you've looked at that offset, you can determine if one will give you the optimal path or not. So to prove the correctness of Graham's scan, because it's a more intensive algorithm, we'll just review. If Graham's scan executes on a set of Q points, again, Q, where Q greater than or equal to 3, again, because that would be your minimum requirement. And the stack S consists from top to bottom exactly the vertices of the convex hull in counterclockwise order. So here, Graham's scan has a bit of the recursion involved in it. It takes a method, evaluates the point at every one, determines which is counterclockwise, and once it has that, then it puts it on top for the minimum distance. So this stacks it on top. And then it moves to the next point and the next, and it keeps modifying the stack. So because you have to constantly evaluate recursively every point, every time you move to a new vertice, Graham's scan can become quite long and intensive. So to modify Jarvis-March was also implemented. Now, Jarvis-March is slightly different and can traditionally be thought of trying to fit a single rubber band on top of these points. So trying to fit a single rubber band, you're not going to go, that mindset won't take you here from P5 to P3 to P1. It'll simply fit the widest point, but at a minimal value. And we'll talk about some of that criteria. So in Jarvis-March, you have a runtime of NH, number of vertices in the convex hull, and again, N is the number of points. So here, in log N, can be very intensive. Jarvis-March is asymptotically faster than Graham's scan because you have the number of points. You're not evaluating every point. You don't have that recursion call. Technique of package GIF wrapping. So while Graham's scan evaluated which angle gave you a cross product sign and which angle did not, Jarvis-March does not have that limitation. And as a result, you can speed up the computation because you're minimizing the number of intersections. Closest pair of points. We'll review some terminology so that we can really define what closest means. Closest here is defined as Euclidean distance. So given two distinct points, P1 and P2, then if we take the square root of the sum of squares differences, we'll be able to calculate a measure of distance. So this Euclidean distance is one way to calculate distance. There's other ones that have been mentioned in other literature of city block and some other ways to calculate distance. So for here, we'll stick with the Euclidean distance to determine it between 2 points, or the Euclidean definition to determine the distance between 2 points. The runtime. So when determining the distance between 2 points, you could go between 1 point and every pair of points. And because you're doing that every time, and you're doing it over the span of every single point for every point, so you're reevaluating it n times for n points, you get n squared if you do this brute force method. If you do a divide and conquer method, you quickly decrease the time to n log n. So what is the divide and conquer method? It is very similar to an approach from merge sort, where we have a base set and divide in 2. Take the next set, divide in 2. So because it's a very similar approach to merge sort, it shares the same runtime definition. So let's look at divide and conquer a little deeper. Again, the runtime is O n log n. So the first step of a divide and conquer is, of course, to divide our set P of points into left and right sides. Then we're going to conquer by calling the distance function twice for the left side and the right side. Once we've determined the distance of those that have been divided, we'll look at the closest pair found by delta in the left and right side. So to give this a better graphical definition, delta being our spanning width, so you'll choose some distance delta, and you'll calculate a vertical line that's. Once you have the vertical line and you apply delta, you wind up with a rectangle 2 delta wide and 1 delta high. So here, inside this rectangle, you now have 1 point on the left side and 1 point on the right side. And you would call the distance function for the left side, and you'd call the distance function for the right side. Now, looking at this definition, you can really start to speed up your evaluation from the brute force method. Because to know if something is close enough, using the same spanning width, so it's got to be at least 1 delta away. So in this case, there's no other one 1 delta down, or in this definition. So if you were to extend this rectangle up, you'd be able to say it's at least within 1 delta, but nothing else is. So if we were to take this rectangle, and extend it up to the next section, you could see that it's still 2 delta wide and 1 delta up. So you would note that on the left side, this is at least 1 delta high and less than 1 delta wide away. So by creating this boxing method, you really limit the number of comparisons you have to do, which in fact, the book points that you only have to evaluate 7 points for each box to determine the minimum or the closest pair. So obviously, determining 7, if n is greater than 7 or more, you really speed up the runtime for this evaluation. So a lot of this logic for the divide does center around keeping a uniform spanning distance and moving the rectangle along this vertical to know that if it's just inside the box or not. So if we move this box up, sorry, but if you were to take the box, this rectangular gray box, and you were to shift it up, then again, moving it, you would see that it's always within 1 delta. So even when this one may look closer, it's not within 1 delta or 1 delta wide when you've distinctly divided your set P points into 2 sections. So this is how the divide and conquer really saves you a lot of overhead time, is by dividing between the two. Finding a vertical line that can divide the left and right side. Then once you've divided that, it recursively calls the distance function. Our distance function here, the square root of the sum of squared differences, and then takes the smallest delta given the spanning, takes the smallest distance given the spanning width that you've just calculated. So again, as you change the spanning width, you may be able to zero in faster than other ones, but you'll always have a smaller subsection. Another point of this is that you're dealing with, this can work very fast on what you could call pre-sorted points. So here we have 6 total points, but if these were in some way sorted beforehand, this rectangular method becomes very quick to use the distance and determine what falls into this rectangle and what does not. So you're basically getting an idea of sorting a sorted array. So you're taking a subset, which would be these 3 points that fall in here, and you're determining which of these is closer. So you're sorting a subset. So that's always important to keep in mind. That is, you can partition this into smaller sections. It can be much faster than this brute force method. Here's an example that we'll be covering in class, but I'd like for you to conceptually see some real-world applications. Say we have a series of points, and we need to find the approximate center of those points. Here's an example. Each one of these points represents a real-world point of electricity delivery. Longitude and latitude locations are given, and you can see how a general shape is made from these series of points. So what we'll do now is use our previously covered method of a convex hull to determine an area, and once we have the area, hopefully determine the center of those points. So just given a general information of a number of points, P of points, a set P where each of these points are real longitude latitudes, we can use convex hull to, such as the Jarvis march covered earlier, where you're kind of wrapping a rubber band around the most outlier points. Now, once you have this area, you can calculate a center point. Center point to look at distances between other similar objects, or you can use that center point to look at distances to other polygons. But how do you know that that center point is very good? Could it be off? Could it be weighted incorrectly? So adding a bit of information, such as a local power company, you can re-estimate individual convex hulls and estimate the center of those convex hulls. So a power company can actually be inside another power company, which is why you have multiple X's inside some of these polygons. And now you've actually cleared out some white space, some empty space, and hopefully can get a better estimation of the true center. So this is what we looked like before, just attributing everybody to one bucket, to TVA. Here, we've attributed the correct points to the appropriate power companies, represented by each of these different purple polygons. Once we have these polygons, we can find the center of centers, if you will, every X here. And here's the difference. So again, the red line represents our every point taken into account equally. This was that center. Now the triangle is the center of centers, if you will. So we're trying to eliminate this white space and not count it as showing up as one of these denser spaces. And triangle represents our new calculated center, which is a much better estimate than the X. And why is this important? Because if you were looking at distances to weather or distances to other geographic ranges, being hundreds of miles off will make a significant difference in how you attribute weather effects or other geographical information. So this element combines a few different points that we will go over in class, such as intersecting lines, convex hulls, and a little bit of data information. Thank you.